In the last class, we come across about the projection of A bar on B bar as A dot B by projection of A bar on B bar dot B bar by modulus of B bar, projection of B bar on A bar dot B bar by modulus of A bar. Then the component vector of a vector R bar along A bar is same as the orthogonal projection of R bar on A bar. Next is given by R bar dot A bar by modulus of A bar whole square into A bar. Next, the component vector of a vector R bar perpendicular to A bar is same as the orthogonal projection of R bar perpendicular to A bar is R bar minus R bar dot A bar by modulus of A bar whole square into A bar. Now let us discuss about, if I take, this is x-axis, y-axis, z-axis. If I take A bar is equal to A1i, A2j, this is A3k. So let A bar is equal to A1i plus A2j plus A3k be the vector then first one A1, A2, A3 are the scalar component or projection of A bar on x, y and z axis respectively. Now look here, if I take A bar is equal to A1i plus A2j plus A3k, I take this is what? A1, A2, A3. A1, A2, A3 are nothing but the scalar component of A bar on x-axis A1, on y-axis A2, on z-axis A3. Or in other words, the projection of A bar on x-axis, the projection of A bar on x-axis is A1, on y-axis A2, on z-axis A3. Then what about the second one is? The second one is A1i, A2j, A3k are the component vectors of A bar on x, y, z axis respectively. Then the third one is A1, A2, A3 are the DRS of a line A bar. Fourth one is A1, A2, A3 are the DCS of a vector A bar. Try to understand. This part is very important. You will get very logical question in the examination. Now if I take A bar is equal to A1i plus A2j plus A3k, this is x, y and z axis, 3 dimension. Now A1 is the component, scalar component or scalar or projection of A bar on x-axis. Similarly, A2, A3 on y and z axis respectively. Later, if I take A bar is equal to A1i plus A2j plus A3k as a line or a ray or a vector. If you want a DCS and DRS treatment, better go for a line or a ray instead as a vector. Now where A1, A2, A3 are the DRS of a line represented by A bar, and A1, A2, A3 are the DCS of a unit vector A bar. Why? Because in DCS, A1 square, it must be unit vector, means L square plus M square plus N square is equal to 1. I mean, A1 square plus A2 square plus A3 square must be equal to 1. For DRS, no need to be. So therefore, this is about the projection or a scalar component or component vector on coordinate axis. Right. Note, if A bar and B bar are two vectors and L, M be two non-zero scalars, then the very first one is minus A bar dot of B bar is equal to A bar dot of minus B bar is equal to minus A bar dot B bar. Next, minus A bar dot minus B bar is equal to A bar dot B bar. Third one is LA bar dot MB bar is equal to LM into A bar dot B bar. Just you take it as results. You do not find much applications on this as a fundamentals. Note, product of vectors satisfies distributive law. Distributive law on vector addition. That is, A bar dot B bar plus C bar is equal to A dot B plus A dot C. This is left distributive law. Second one is B bar plus C bar dot A bar is equal to B dot A plus C dot A. This is right distributive law. Let us see how you find out. I'll give the proof for left distributive law. Let us start. Proof of this one is, if I draw a figure, OA bar is equal to A bar. Now, OB bar is equal to B bar. BC bar is equal to C bar. Then, by using vector addition, if I join these two, this is nothing but B bar plus C bar. I start. Let OA bar is equal to A bar, OB bar is equal to B bar, BC bar is equal to C bar, be three vectors by vector addition OC bar is equal to OB bar plus BC bar, OC bar is equal to B bar plus C bar. Now draw perpendicular, it's a B dash, C dash. Let B dash comma C dash be the feet of perpendiculars from on OA from B and C respectively. B and C respectively. Therefore, now I can write OB dash, OC dash, that is OC dash instead of okay, OB dash, BC dash be the projections of B bar and C bar on A bar. OC dash be the projection of B bar plus C bar on A bar. Therefore, by vector addition, OC dash bar, OB dash bar, B dash C dash bar. Okay, or else this is by vector addition. Or OC dash is equal to OB dash C dash, which implies OC dash is a length, is equal to total length is equal to sum of these two small lengths, OB dash, B dash, C dash. Lengths are nothing but a projections. Therefore, what I do is projection of B bar plus C bar on A bar is equal to sum of projections of on A bar. Now, which implies I can write, as I told earlier, the projection of A bar on B bar, denominator must have B bar, A bar dot B bar by modulus of B bar, or the projection of B bar on A bar is A bar dot B bar by modulus of A bar. B dot A or A dot B. A dot B is equal to B dot A. Wherever you want, you can take it. So, therefore, now I can write B bar plus C bar dot A bar by modulus of A bar is equal to B bar dot A bar by modulus of A bar, C bar dot A bar by modulus of A bar. What is this? This is the projection of B on A. What is this? Projection of C on A. That's what I wrote it. Sum of the projections of B bar comma C bar on A bar. In the denominator, you have modulus of A bar common. I can write B bar plus C bar dot A bar is equal to B dot A, C dot A. Yes, we verified this is the condition. This satisfies the right distributive law. We can also prove left distributive also. Followed? That's right. So, therefore, now the product of vectors satisfies distributive law. You can go similarly, you can prove the what? First result also. Right? Note, if A bar comma B bar comma C bar are non-zero vectors, and A dot C is equal to B dot C, then A is equal to B or A minus B is perpendicular to C bar. We have to prove that. Now, given A bar comma B bar comma C bar are non-zero vectors. Since A bar dot C bar is equal to B bar dot C bar, which implies A dot C minus B dot C is equal to 0, which implies A bar minus B bar dot C bar is equal to 0. Case 1, A bar minus B bar dot C bar is equal to 0. A bar minus B bar dot C bar is equal to 0, which implies A minus B is equal to 0, C bar is equal to 0. Since C bar is a non-zero vector, A bar minus B bar can be a vector, which implies A minus B is equal to 0, A bar is equal to B bar. Followed? We arrived at this condition. Next, now if C bar is not equal to 0, which implies is perpendicular to what? C bar. Perpendicular to C bar. Followed? So therefore, now according to this, now if A bar minus B bar dot C bar is equal to 0 means both must be equal to 0, since C bar is a non-zero vector. C bar is a non-zero vector. Therefore, this is not equal to 0. What must be equal to 0? Any one must be equal to 0. A bar minus B bar is equal to 0. So A bar is equal to B bar. If C bar is not equal to 0, so therefore A bar minus B bar is perpendicular to what? C bar. If C bar not equal to 0, even you can take A bar minus B bar not equal to 0, then A bar minus B bar is perpendicular to C bar. How? I told already, whenever the dot product of any two vectors is equal to 0, then they are perpendicular to each other. Perpendicular to each other or orthogonal to each other. If the angle between the two vectors is what? 90 degrees, then they are orthogonal to each other. Right. Note, if A bar is equal to A1i, A2z, A3k, B bar is equal to B1i, B3k, then A bar dot B bar is equal to A1 B1 plus A2 B2 plus A3 B3. Let us see how this is. We know that I dot I, J dot J, K dot K is equal to 1. So, I dot J, J dot K, right. Now, the reason, the content of this is whenever the angle between the two vectors is not given, how to obtain the angle, that is dot product of two vectors. So therefore, now what I do is A bar dot B bar is equal to A1i, A2z, A3k dot B1i, B2z, B3k. Now, you take dot product this with this, this with this, this with this. A1 B1 into I dot I, A1 B2 into I dot j, A1 B3 into I dot k, plus this with every vector, A2 B2 into z dot j, A2 B1, A2 B1 into j dot I, A2 B2 into z dot j, A2 B3 into z dot k, plus A3 B1 into k dot I, A3 B2 into k dot j, A3 B3 into k dot k. By using this, I dot I 1, I dot j 0, I dot k 0, j dot I 0, j dot j 1, j dot k 0, k dot I 0, k dot j 0, k dot k 1. Therefore, A bar dot B bar can be written as, this is 1, A1 B1 into 1, this is 0, this is also 0, 0, A2 B2 into 1 plus 0, here 0, here 0, A3 B3 into 1. So therefore, A2 B2 this we arrived at. So therefore, this is ordinary dot product when the angle between the two vectors is not given. Just fundamental definition, I dot I is equal to 1, j dot j is equal to 1, k dot k is equal to 1. Meanwhile, I dot j, j dot k, k dot I is equal to 0. By using that, we could prove as A bar dot B bar as A1 B1 plus A2 B2 plus A3 B3. Followed? Right. With this definition, note 2. Let theta be an angle between two vectors. Then cos theta is equal to by modulus of A bar into modulus of B bar, which implies theta is equal to cos inverse of A bar dot B bar by modulus of A bar into modulus of B bar. When you know cos theta, note 3. If theta is equal to 90, then which implies cos 90 is equal to 0, which implies 0 is equal to A dot B by modulus of A into modulus of B, which implies A dot B is equal to 0, which implies A1 A2, okay, A1, I have taken A bar and B bar. So if A bar is equal to A1I, A2J, A3K, B bar, I can write A1 B1 according to this, A1 B1, A2 B2, A3 B3, is equal to 0, which implies A bar comma B bar are perpendicular vectors to each other, perpendicular to each other. Next, note 4. If theta is equal to 0 degrees, which implies cos 0 is equal to 1, therefore 1 is equal to A dot B by modulus of A into modulus of B. After simplification, you get A1 by B1 is equal to A2 by B2 is equal to A3 by B3. A1 by B1 is equal to A2 by B2 is equal to A3 by B3. Means when two vectors are parallel, when two vectors are parallel, which implies A1 by B1 is equal to A2 by B2 is equal to A3 by B3. Followed? Students, by using the fundamental definition of dot product when the theta is not given, we established A dot B is equal to A1 B1 plus A2 B2 plus A3 B3. After knowing that, when theta be an angle between the two vectors, cos theta is equal to A bar dot B bar by modulus of A bar into modulus of B bar, which implies theta is equal to cos inverse of A bar dot B bar by modulus of A into modulus of B. If theta is equal to 90, then the two vectors are perpendicular to each other. Then A bar dot B bar is equal to 0. According to this, A1 B1 plus A2 B2 plus A3 B3 is equal to 0. Now, if theta is equal to 0, then the two vectors are parallel. Then we can establish A1 by B1 is equal to A2 by B2 is equal to A3 by B3. If A bar and B bar, if A bar, B bar and C bar are three vectors, then the very first one is modulus of A bar plus B bar whole square is equal to mod A whole square mod B whole square 2 into A bar dot B bar. The second one is modulus of A bar minus B bar whole square is equal to minus 2 into A bar dot B bar. The third one is modulus of A bar plus B bar plus C bar whole square is equal to modulus of A whole square plus modulus of B whole square plus modulus of C bar whole square into A bar dot B bar, B bar dot C bar, C bar dot A bar. Students, I told in the beginning of the what? Dot product. One note I told. What is it? Before starting of this proof, I told one note. What is that? A bar dot A bar. It's a good note. Wherever, whenever you want the proof in a simpler way or solution in a simpler way, you can make use of this property. It plays a vital role. and bringing the solution into what curtailed step. So therefore, a bar dot a bar is equal to modulus of a bar into modulus of a bar into cos 0 degrees. The angle between the what? The same line, a line with a line, same line is what? 0 degrees. Or else angle made by the x-axis with x-axis, a line with a line, is always 0 degrees. Therefore, now this I can write this one as a dot a mod a into 1, which implies a bar dot a is equal to mod a whole square is equal to a bar square. This is a very important note. By using this, I can make use of this. By using this, I can write like this. This is nothing but this. Now, first one is modulus of a bar plus b bar whole square is nothing but modulus of, okay, I will write this one as a bar plus b bar whole square. Addition of 2 vectors is a 1 vector. Addition of 3 vectors is a 1 vector. You can add any number of vectors. You can add any number of vectors. But it gives to what? Only 1 vector. Therefore, you expand this a bar square, or else I'll write this one as, instead of expanding, I will write, so we are here, I will write this one is, let us give still vector treatment for this. Now I can write, take the ordinary dot product, a dot a, b dot a, this with this with this, plus a dot b plus b dot b. Now I can write is equal to, what is a dot a? I can write this mod a whole square. Now a dot b and b dot a both are same. Since a dot b is equal to b dot a, both are scalars. So therefore, I can write modulus of a bar plus b bar is equal to mod a whole square mod b whole square plus 2 into a bar dot b bar. In the same way, modulus of a bar minus b bar whole square can be written as okay, now this is equal to, a dot a minus a dot b, b dot a plus b dot b is nothing but a dot a mod a whole square minus a dot b, a dot b. Why? A dot b is equal to b dot a plus modulus of b whole square yes, we got it. Modulus of a bar minus b bar whole square is equal to mod a whole square plus mod b whole square minus 2 into a bar dot b bar. Next we have arrived with this one, a bar plus b bar plus c, modulus of a bar plus b bar plus c bar whole square. Let us see. Third one is modulus of is equal to yes, a bar plus b bar plus c bar. This is nothing but this with this. A dot A dot B, A dot C. Next this with dot B dot A, B dot B, B dot C plus C dot A, C dot B, C dot C. Now I can write A dot A mod A whole square, A dot B, A dot C is same as C dot A, B dot A is same as A dot B. This is mod B whole square. This is B dot C, C dot A, B dot C, C dot B is same as B dot C, mod C whole square. Now mod A whole square, mod B whole square, mod C whole square, A dot B, 2 into A dot B plus B dot C, B dot C, B dot C, C dot A plus C dot A. I can write C dot A. Yes, it has much applications in dot product. In dot product, what it is? Modulus of a bar plus b bar plus c bar whole square is equal to mod a whole square plus mod b whole square plus mod c whole square is equal to 2 into a dot b plus b dot c plus c dot a. C dot A.